Section 12.8 considers what's known as residual test, or test about the error terms. So if you recall, when we began the discussion of simple regression, we said that the error terms, we're going to assume that they're normally distributed and that they have a constant variance. Having a constant variance is also called homoscedastic errors. Okay, and the problem when errors do not have a constant variance is known as heteroscedasticity. Okay, so these are two problems that we'll think about. We'll think about the first one just briefly because a violation of non-normally distributed error terms is usually not that big of a deal. But the second problem can be a big deal. The third problem that the book mentions is when the error terms are not independent. Okay, autocorrelated errors is a problem that's particularly a nuisance in time series regression. And we're going to save that section for when we get to chapter 14. Okay, so non-normal errors. There's two components to this. There's something that's not a problem. The parameters and standard errors are going to be unbiased and consistent. And that's the good news. The problem is non-normal errors can bias your confidence intervals and your prediction intervals because we're assuming normality for the t statistic, the t distribution that we're using to construct those confidence intervals. Okay. Usually, if you have large sample sizes and if you trim outliers, which we'll talk about what this means in just a second. Let's see, I should put section 12.10. Okay, then you can solve a non-normal problem. But to detect it, we need what's called a normal probability plot. Okay, so let's say we're in Microsoft Excel. And let's see. There we go. And just to emphasize, the book tells us that non-normality is not considered a major violation because the parameter estimates remain unbiased and consistent. Don't worry too much about it unless you have major outliers. Okay, and we're going to follow those guidelines. We're not going to worry about checking the normality assumption violation when we estimate our regression models. But if you do have big outliers, it's probably a good idea to check that. Okay, so let me just walk through how that's done. So in your data analysis function, if you click on standardized residuals, and along with the regression output, you'll get a table of values. And so here's a busy slide that illustrates how to construct a normal probability plot. So for that wait time and number of operators data, I clicked on the standardized residuals box, clicked OK, and the output that you get is this residual output. You can see that the residuals, this third column, these are the numbers that we calculated in Excel by hand. And then the standardized residual is this last column. Okay, these standardized residuals is the residual divided by the standard deviation of the residual, of the error term. Okay, so what Excel does, it divides each of these numbers by the standard deviation of this column. And this normalizes the residual so that it's between -3 and +3. And this is the same -3 and +3 that we've talked about when we talked about the empirical rule. Okay. So to find the normal probability plot, you sort these numbers from low to high and then insert a scatter plot into your output. So I sorted this last column from lowest to highest. So the lowest number is -1.12, and there you see that dot. The next lowest is -0.81, and there it is. The We have got the third lowest standardized residual is 0.04, and there it is. The fourth standardized residual is 0.57, and there it is on my plot. And then the highest one is 1.33, and there it is for the fifth observation. Okay, so then I clicked on the dots, inserted right mouse clicked, inserted a trend line, and then clicked the button to show the R squared on the diagram. Okay, and the R squared for this regression line is 0.98, and since that is very close to 1, we would say that these error terms are normally distributed. Okay, a trickier problem is when you have heteroscedasticity or heteroscedastic errors, and this is when the size of the errors, the residuals, depend on the independent variable. Okay? It's not a problem for our parameter estimates. It's not a problem for our slope estimate. It's still unbiased and consistent. The problem is that our standard error is going to be biased. The standard error is going to be too low. It's biased downwards. Biased downwards. I should put that in the slide. Biased downwards standard error. And that means our t-statistics will be too high. So a lot of times we might think that our slope coefficient is different from 0, statistically different from 0, when in fact it is not. Okay, so you can find that with residual plots. And if you think, and there's some other tests, but for stats 2, this level of statistics, we're just going to do residual plots. If you think you have heteroscedasticity, you can, one simple thing to try is to transform both of the dependent variables into a different functional form. You can try the natural log, okay, which we'll talk about later on in this chapter and also in chapter 13. A lot of times what's known as a double log model solves a heteroscedasticity problem. So this is what heteroscedasticity looks like. So this is called the fan out pattern that indicates heteroscedasticity. So on the horizontal axis we have plotted the number of square feet of a house. So this is a home price regression where the dependent variable is home price and the independent variable is square footage. And on the vertical axis we've plotted the standardized residuals. Okay, and you can also plot just the raw residuals themselves. But as you can see, as you go from left to right, the vertical distance between the lowest residual and the highest residual increases. And that's called the fan out pattern. Okay, some residuals that don't exhibit the fan out pattern look like this. So we've got the x value, whatever that is, and then here we've got plotted the raw residuals this time, and it looks like those are randomly distributed along the 0 line. So in this case we would conclude that there are no heteroscedasticity problems. To compute to get a residual plot in Excel, if you click on regression and click on residual plot down here in the residuals box, the output that you get will be what you need. So here we have the independent variable on the horizontal axis and the raw residuals plotted on the vertical axis. And we don't have enough data to recognize any sort of pattern, but with more data we can get a feel for if we have heteroscedasticity or not. And we'll look at some examples in a little bit or in a later lecture.